Previously, when uh, we started talking about the basic concepts of modeling using the eddy viscosity and Boussinesq assumption, the fact that we can calculate the Reynolds or turbulence stress, which is an artifact of the mathematical averaging process, but we don't know exactly what is the physics. So it does have a unit of stress, and people talk about computing the stress from a strain rate, similar to what solid people are doing, and similar to what we do in calculation of viscous stress, which is a physical or real stress. Effects of turbulence, I mean all eddies on fluid particles are perceived as stress, and it does appear in the equation and we are trying to model it. So people say let's use the strain rate. In fluids, we do not use a strain itself, we use its rate. And relate it to the stress using a constant. And this constant is called eddy viscosity. And all turbulence modeling attempts, like those algebraic models, one equation, two equation, turbulent kinetic energy based models, their entire effort is to obtain a value for eddy viscosity or nu T. Because it has a unit of viscosity, meters square per second, people thought of using a time scale multiplied by a velocity scale, and they proposed the parental length scale and these things. So we just talked about all of these stuff there, the eddy viscosity and stuff, but uh, there was this thing that uh, we just proposed that in the 2D boundary layer flow is u star will be equal to uh, mixing length time the velocity mean velocity gradients du dy, and there is a problem that if you have some sort of flows that you don't have any velocity gradient, meaning that your du dy is zero, like in here, then using the mixing length based models will give you the u star equal to zero as well. And this is not necessarily true. You might have many different types of flows where you have somewhere in the flow with zero mean gradient, but u star uh, is not zero, and therefore eddy viscosity and therefore turbulent stress is not zero. It's a big handicap of this type of mixing length based models. Especially, uh, it is found over the years that the mixing length based models are not correct for decaying grid turbulence and also measurement in a round jet center line where your nu t is not equal to zero. Therefore, these models have Therefore, these models have some kind of inconsistency. So people started to look for other types of approaches. Instead of using uh, equation u star equal to uh, lm du dy to calculate the u star actually, people suggested to use turbulent kinetic energy, K, and you know that its unit is velocity squared, meter squared per second squared. So people say that okay, let's take its square root and calculate the characteristic velocity u star from there. So k to the square root of k times some constant will give you the characteristic velocity. This was a starting point of all turbulent kinetic energy based turbulence models. This was even proposed long before the actual computer implementation and development of K epsilon models and everything. It was, in fact, proposed by Kolmogorov back in 1942 and also by Prandtl back in 1945. And this was proposed to calculate the velocity scale U star there. For the length scale L star, they said, okay, let's keep it there and use it as it was. So if L star is equal to Lm, then your new T would be constant times turbulent kinetic energy, square root of turbulent kinetic energy times uh, Lm, which is similar to algebraic models. There has to be an input of Lm, so it is pre-specified. Uh, the distribution of Lm into your model is pre-specified. So it is you start the numerical integration after specifying Lm. In addition to that, there has to be you need to use turbulent kinetic energy because you use it in here to calculate your U star, and these types of models are called uh, one equation models since it forces you to calculate K. You need to calculate K, turbulent kinetic energy, for which you need to solve additional partial differential equation, uh, which is governing equation for K. So we will talk about this governing equation, but first of all, let's see the steps of implementing these one equation models. First, you have to pre-specify mixing length. So, in at each time step and at all points in your grid, you have to pre-specify value for your mixing length. After that, you have to solve the model transport equation for K. So what you see in here, as you saw before, it is the exact transport equation. In here, I'm talking about a model transport equation. We will talk about it. After solving this model transport equation, you calculate nu from this equation. So you have the constant, you have the turbulent kinetic energy, you pre-specified Lm, so you can calculate nu. And then obviously after having the value of nu t, you can obtain your Reynolds stresses, and then you can solve the equations to obtain distribution of velocity and pressure, mean velocity and mean pressure. After obtaining these, your mean velocity, your mean pressure, your mixing length, turbulent kinetic energy, eddy viscosity, and Reynolds stress are all being obtained. I put model in, uh, let's say, quotes because we have derived before the actual transport equation for K. And in the left hand side, you see that it includes time derivative and convective derivative for K. And on the right hand side, which is in here, this is right hand side of the exact K equation. You have the flux divergence term, you have the production term, you have the dissipation term, and this is the actual transport equation that theoretically was being derived. But that equation has many, many unknowns. You look at this equation, there are too many unknowns there. So we develop a new modified transport equation, which we call it a model transport equation. I'm talking about second step, solve model transport equation. Let's say we solved this model equation numerically, and then you go back to the definition of nu t, and you calculate it. So you have the distribution of k, and you have the LM, so nu t will be known for you. So if you follow these 6 steps, it means that you just kind of get all the variables that you need. One thing is critical in here, since everything starts with the mixing length definition. See, step 1, mixing length definition. uh, you really need to have some idea about how to specify this mixing length, and it heavily depends on geometry and flow. So every mistake you do in first step, it will show itself in the final solution. So you have to be careful about this as well. Another critical step to model transport equation for turbulent kinetic energy will be examined here. First of all, I'm writing the exact equation for K, meaning that the equation that is derived mathematically from theory. In other words, we have original instantaneous momentum equation, we do the decomposition, we apply the decomposition, multiply terms and take average, and then we obtain the average momentum equation. And you remember from that equation, we could obtain the exact equation for turbulent kinetic energy. So uh, this is that equation, exact equation. What do we have in here? dk dt plus the uh, convective derivative, and you have the flux divergence, you have production, you have dissipation, and inside the flux divergence you have this Ti prime, which includes these 3 terms. So what you have to think about this equation, there are some terms in this equation that we don't know in this uh, K exact equation. We have no idea about their physics. For example, this triple correlation, Ui, Uj, Uj, you see it. Or the correlation between velocity and pressure, this UIP, or the correlation between velocity and strain rate, UJ, So this equation becomes a very big headache because we cannot solve it. Literally, solving the exact equation of K transport is not possible. Therefore, we will replace on all these unknown terms with model terms, and we hope that they are able to represent the physics as we want. This P is a production or rate of production, which is nothing but Reynolds stress times mean strain rate. And in order to obtain the mean strain rate, we need the mean velocity field. So the components of production are all known values. So we just need to multiply Reynolds stress with mean strain, and there is no need to replace the P or production with any model term. Epsilon is another problem because it includes viscosity, which is luckily known, as well as strain rate fluctuations that those are unknown and need to be replaced by model terms. So at the end of the one time step or one iteration, at the left hand side of this equation in here, we have the k, which is known, we have ui bar, which is known. So the conclusion is that we cannot really use the exact equation, and we develop what we call a model equation. If you look at this equation again, right now we look at the K equation, but it is something general that we do in modeling. We investigate the terms one by one in the whole equation. And there is a term that we call it a closed form. Any term that is completely determined by nouns is said to be in closed form. For example, a list of nouns that we have, the list of variables that we have, ui prime, p prime, l, m, k, nu, t, and Reynolds stress, ui prime, uj prime bar. The closed form is actually a technical term. For example, in production, P, production is in a closed form, because, meaning that it is calculable with the known variables during the integration of equations. Actually, this is not unknowns, this is nouns. But this epsilon and also ti prime are not in closed form. When you determine which terms are in closed form and which terms are not, you can develop some studies accordingly. Again, look at this equation. In here, the whole left-hand side is in a closed form because you already know your k, you already know your velocity distribution. So I can write the whole thing in here as capital dk dt, and also the production are in closed form. They don't cause any problems, but you have the gradient of ti prime and you have the epsilon that are not in a closed form and should be, you should do something about these terms. Okay, there are two ways to tackle this problem. One way is more or less a spectral way. So we don't know epsilon. Let's produce another partial differential equation to solve epsilon. So that equation before what this equation that we are talking about is the K equation, and in addition to this equation, you will introduce another equation that solves for epsilon, and those models will be called two equation turbulent kinetic energy models. Before going there, we can also do something simpler. We can propose another equation, but this equation is not a differential equation to calculate for epsilon. Okay? The idea is this. From all the physical properties we have discussed, we know that the order of magnitude of epsilon is u0 cubed over L0. You remember that this u0 was your integral velocity scale, L0 was your integral length scale. So using this simple argument, we can propose a simple equation to calculate epsilon. What people proposed is that for the velocity scale, u0, let's use the square root of k. So instead of u0, put a square root of k. So u0 cubed will be k to the power of 3 over 2. And for the length scale, let's use the pre-specified uh, Prandtl length scale, Prandtl mixing length, Lm, for the length scale. And to make the proportionality to an equality, since you have k to the power of 3 over 2 over Lm, will not give exactly the epsilon, let's multiply it by a constant, and let's call this constant Cd. So epsilon is equal to Cd times k to the power of 3 over 2 over Ln. This was the first approach to come up with an additional equation for epsilon. Of course, let me check. Of course, uh, We don't know what exactly CD is. If you do this, then epsilon becomes enclosed form. So you know this K, you know the LM pre-specified at least. So if you know CD, epsilon will be also enclosed form. We call this equation a model equation for epsilon used in uh, one equation turbulent kinetic energy models. And according to nu t equal to ck square root of k times lm, you can calculate nu t right now. After this proposition, people back in 1960s and 1970s tried to do different experiments to come up with appropriate CD values, these constant values. And mostly they used hot wire anemometry and LDV laser Doppler velocimetry. And in different types of turbulent flows, they tried to measure turbulent kinetic energy, K, and try to estimate epsilon using different techniques based on a stress field to calculate nu t from the model equation as well. And the actual equation for nu t that it is because nu is Reynolds stress over mean strain, right? Then if you do the experiment and you measure the Reynolds stress in here and you measure the mean strain field, this means that you are measuring the turbulent viscosity, actual turbulent viscosity. Then you can see what these constants CCD, C times CD are. Using DNS, you can also do the same thing to find the constants, and people have actually done that and found something like this. So this is figure 10.3 in Pope's book, the DNS data of fully developed turbulent channel flow. Okay, a specific flow. The vertical axis is actually your C over CD because it is nu times epsilon over k squared. So the vertical axis is actually your constant thing in here. And the horizontal axis is your y plus. This is related to wall boundary layer DNS. Then they see that, okay, this CCD or this constant increases first and then converges to values around 0.09. You can see it in here. What happened to my... it converges to some number around 0.09. So except very close to the wall, which is uh, kind of y plus smaller than 50, except this in this region, uh, this value converges to a constant value. So this was one case, and it's nice and it gives very quick solution to epsilon. And your computer code is going to run and converge very fast if you put C times CD equal to 0.09. But within the boundary layer less than 50, I mean, when you are here within this region, this will generate some solutions, but we cannot rely on it. This is only DNS data for a specific turbulent flow. It is a channel flow and it is fully developed. This is not the only type of flow in the engineering world. There are thousands of different types of flows. And is this model going to work for those flows as well? This is the question. We don't know. We usually do this way. We do the simulation, we try to find validation test cases, we run the simulation and check if the results do or do not match, and then we start to tune these parameters and try to match it. It's a kind of cheating if you know the solution you will make Actually, you will make sure your computation will match that solution. In the engineering world, that is how we work, unfortunately. If you don't know the solution, that is a problem, because we will have a problem on what to use for these coefficients. This figure is for channel flow, but if you want to do computation around a wing, you have to do, you have actually, you, you have no idea of what is this CCD in that case. You just tuned it in some test cases, but it will not guarantee that it works in some other test cases. These are fundamental problems in RANS-based calculations. So, so far, what we solved is only the dissipation in this equation. So what we just solved the dissipation. We don't know the flux divergence term in here. We don't know anything about this Ti prime. And we have to produce a model equation for the flux divergence term as well. Actually, it's a long process, and if you want, you can read about it in the Pope's book yourself. But generally, Ti prime is modeled with a gradient diffusion hypothesis. It's very critical that you understand what is gradient diffusion. You know, the Ti prime is a flux type, and its actual value gets influenced because of the three terms. So if you go back to the Ti prime definition, it has triple correlation. It has velocity pressure correlation. It has velocity and strain correlation. So this thing, what you see, these are the terms that are affecting Ti prime. But in here, in the equation of transport equation of k, you see that Ti prime also affects this k. So uh, it does not produce k, it does not destroy k, it only changes the distribution of k, because it is ddxi of Ti prime. So it only changes the distribution of k in a space, and actually it tries to evenly distribute turbulent kinetic energy in this space. So physically, it represents fluxes of the terms in the right hand side, fluxes of these terms in the right hand side by moving from one point to another point for an existing turbulent state. Okay, people said that if this is a flux term, this Ti prime is a flux term, the diffusion of this flux term should occur along the gradient lines of K. What I mean, if K is, let's say, high at some point and it is low at some other point, K will flow in that direction, right? As well as Ti prime. So Ti prime also flows in that direction. We don't actually, we don't uh, question how this flux is produced. We accept that there is a flux, then we say that this flux will follow the K gradient. Okay? This is gradient of K will be vector. You know this is a vector. There is a gradient. You remember the gradient of pressure, which is a vector with direction. So this is the same. It has three directions. So we say this flux will follow that direction. What I just described is called gradient diffusion hypothesis. If this hypothesis is true, then instead of all these complex triple correlation, pressure velocity correlation, and etc., you just replace them with a very simple equation. And this equation will be in a closed form. So what I just wrote in here is that simple equation. Ti prime is equal to minus nu t over sigma k times ddxi of k. And the sigma k is the turbulent Prandtl number, which is around 1 for most air flows. So basically, we made this assumption that the flux of Ti prime will get diffused along the gradient of k. So we replaced it with gradient of k. You see, this is the gradient of k. With appropriate terms, these are the terms to make the units matched. So it has to be matched from left hand side and right hand side. So this equation is in closed form, as you see. Everything you know sigma k, it is 1, you know nu t, you know your k distribution, so it is in closed form. And at the end, we arrive to the model transport equation of k. So in here, we just solved the epsilon problem, and you just replaced ti prime with these. So uh, right now, uh, this is a complete set of equations that you need to solve to obtain the second step, this model transport equation for K. This is a one equation model since there is only one PDE in here. So you see only one PDE in here, and there are two algebraic equations, this one and this one. So they are simple and very quickly solvable numerically. But one equation model similar to algebraic model we discussed before, uh, it is still incomplete due to LM. So you have to again pre-specify mixing length because this length needs to be specified at the beginning of the solution. The solution to this problem actually came in early 1970s, and the idea was, okay, let's put one more step by keeping the K transport equation, this equation, model transport equation for K, instead of simplifying epsilon, instead of it, let's derive another transport equation directly for epsilon and solve this. Although the analytical or the exact transport equation for epsilon is very, very complex than the equation for k, as we will see in a moment, we can do this. So again, we need to replace it with a model transport equation, and it will be called k epsilon model. And once you can solve these two transport equations, the distribution for k and epsilon will be obtained. So without the need for this mixing length specification, you can determine your nu t value, because you remember your nu t was k over epsilon. And we will see how we do that in a moment.